the day gravity glitched over Antarctica. Right now, hundreds of kilometers above your head, some of the most precise machines humanity has ever launched are drifting off course. They are not failing. They are not being hit by debris. Their orbits are being tugged ever so slightly by a patch of Earth that refuses to behave. Again and again, the error traces back to the same place on the globe, a cold white corner at the bottom of the map, West Antarctica. These are gravity mapping satellites, descendants of missions like GRACE and GOCE. They do one thing with obsessive focus. They feel how hard Earth pulls on them, measuring tiny changes in the planet's gravity field as they fall endlessly around it. For most of the world, those measurements line up with expectations. Mountains pull a bit harder, ocean basins a bit less. The equations work. Over West Antarctica, they do not. There, buried under kilometers of ice and rock, something is so massive and changing so quickly that it is literally rewriting the local gravity field. The pull of Earth is not a fixed background anymore. It is a moving target. Maps that once showed a smooth, reliable tug now have to be redrawn, the contours warping over time, as if the planet itself were breathing. This is not an explosion. There is no plume on satellite images, no shockwave, no headline-friendly disaster. This is a quiet event written in millimeters per second and microgals of acceleration. The force that keeps the oceans in their basins and keeps you in your chair is shifting in silence, and that silence should feel more disturbing than any sudden bang. Because when gravity changes, even a little, the consequences ripple outward. Water flows differently. Sea level doesn't just rise. It redistributes, subtly tilting toward or away from coasts that thought they understood their fate. Satellite orbits stretch and sag, forcing constant corrections. The entire Earth wobbles. Its axis of rotation nudged the giant spinning machine of the planet ever so slightly rebalanced. We are watching, in real time, a fundamental force redraw the rules beneath one of the most remote places on Earth. This frozen continent, which from orbit looks like some of the emptiest, coldest space anywhere in the solar system, is quietly exerting a new kind of influence on the rest of the world. Is this only ice melting, mass slipping from land into ocean as the climate warms, or is something deeper waking up beneath the South Pole, ancient buried mountains, rising mantle rock, perhaps a scar from a cataclysm a fraction of a second after the birth of the universe in geological terms, now tugging on the entire planet? To answer that, we have to peel back the ice and read the hidden gravity scars written into the bedrock of Antarctica itself. When the world's most precise scales start to disagree, you grow up with a comforting illusion. Gravity feels like a constant and invisible contract that never changes. The same pull on your body whether you stand in a desert, on a mountain, or at the edge of the sea. It is the quiet background of existence. It is not really. Underneath that apparent stability, gravity is a lumpy, restless field, sculpted by how mass is arranged inside the planet. Pile up a mountain range, and the extra rock tugs a little harder on passing particles. Carve out a deep ocean trench, and the missing mass softens the pull. Even slow rivers of hot mantle rock creeping beneath the crust, and ice sheets that thicken and thin over thousands of years leave subtle fingerprints in the way the Earth grips everything around it. To see those fingerprints, humanity built something extraordinary, scales that orbit the planet. GRACE was a pair of satellites chasing each other around the globe, measuring their separation to micrometers as they flew through some of the emptiest, coldest space anywhere in the solar system. When they passed over a region with extra mass, the leading satellite was tugged ahead, the trailing one fell behind, and that tiny change became a map of gravity. GOCE went further. It skimmed the atmosphere in an ultra-low orbit, forever on the edge of falling, its instruments feeling every wrinkle in Earth's pull. Where GRACE sensed broad swells and hollows, GOCE traced fine structure, turning the entire planet into a kind of X-ray image of hidden density. Scientists knew the field would not be perfectly smooth. They expected a gentle patchwork, a little extra pull over the Himalayas, a slight deficit above the Mariana Trench, the ghost of old mountain belts buried beneath continents. These variations were supposed to be small corrections to models they already trusted, refinements that would help predict how an ice sheet should sag, flow, and melt over decades. What they did not expect was for those scales to disagree with the ice itself. Over West Antarctica, GRACE and GOCE saw more than gradual loss where glaciers were pouring into the ocean. They saw a dark, shifting scar in the gravity field, a region where mass was vanishing as ice thinned, but also strange pockets where gravity was increasing, as if something heavy was rising from below to replace the missing ice. The crust there seemed to be rebounding too fast, the mantle responding too eagerly, the whole system behaving less like a passive cap of frozen water and more like a living joint in the planet's skeleton. There was no emergency press conference, no viral headline declaring that Earth's gravity was misbehaving. Just a spreading unease in technical papers, conference corridors, and late-night data sessions as independent instruments kept returning the same message. Antarctica was not following the script. If our best orbital scales say the ground itself is shifting under the ice, what exactly is waking up beneath the South Pole? A planet that refuses to sit still. For most of our history, the answer would have been simple: nothing. The ground was the ground. The sky was the sky. Gravity was just there. For hundreds of generations, humans treated Earth as a solid stage, a heavy, indifferent platform on which history unfolded. Mountains might crumble, rivers might carve new paths, coastlines might drown or emerge, but the weight of the planet itself was assumed to be fixed, the pull of down a permanent backdrop to everything that breathed or moved. Modern civilization took that quiet assumption and industrialized it. Skyscrapers lean on the conviction that the bedrock under their foundations will not subtly exhale. GPS satellites trace their orbits through some of the emptiest, coldest space anywhere in the solar system on the belief that Earth's mass is a stable target, that the invisible well of gravity beneath them will not twitch from year to year. Power grids, seawalls, undersea cables, the flight paths of aircraft, all of them depend on the idea that the laws of physics are not merely universal, but practically unchanging on human timescales. We built a planet-spanning nervous system of sensors and timing signals on that faith. Then Antarctica began to whisper that the faith was misplaced. GRACE and GOCE, two satellite pairs that fly in a tight gravitational dance, were designed as a kind of orbiting seismograph, feeling tiny changes in Earth's pull as they rush through the cold vacuum. They were not the most powerful machine humanity has ever built, not a cathedral built to worship a single question, but they were exquisitely tuned to one thing: mass. When they passed over West Antarctica, the signal dipped again and again. The ice sheet was losing weight so rapidly that the very shape of Earth's gravity field was sagging in real time. In other words, the planet was forcing our most precise machines to constantly relearn what down means over the poles. Gravity, the most taken for granted force in the universe, was no longer a static background. It was a moving target. That shift is not just a climate story, it is a philosophical ambush. If melting ice can redraw the gravity field, if isostatic rebound can make the crust rise centimeters per year, if mantle flow and buried rift systems can redirect the deep currents of rock beneath Antarctica, then the boundary between climate change and planetary reconfiguration begins to blur. We are not only warming air and water, we are nudging the hidden machinery that shapes the entire field in which oceans, continents, and orbits make sense. And there is a darker implication hiding at the edge of the data. The gravity anomalies, the accelerating uplift, the unstable ice streams, may be early hints that this system has thresholds, tipping points in ice, rock, and mantle flow beyond which our models stop being reliable and our intuition about a stable Earth simply fails. Because if one frozen continent can rewrite gravity on the fly, the next question is unavoidable. How far can this go before the planet crosses a line it cannot quietly step back from? So we need a new way to think about this continent, not as a blank white cap, but as a sleeping scar. West Antarctica is a wound in the planet's crust that never fully healed, stretched and torn when ancient supercontinents split, stitched together by rifts and faults, and then buried under ice so thick it can hide entire mountain ranges for tens of millions of years. The surface is silence. Underneath is a frozen archive of violence. In this scar, the crust is thinner, the mantle closer, the rock fractured into basins and ridges that channel ice the way a hidden tunnel system channels water. GRACE and GOCE did not just see missing ice, they saw this broken architecture bending Earth's gravity itself. To understand why the field is warping now, we have to walk the scar from its origin to its possible future. First, we descend through 3 and 4 kilometers of ice through some of the emptiest, coldest space anywhere in the solar system to the ghost continent below. Radar and gravity surveys sketch out mountain belts as high as the Alps, like the buried Gumbertsev Range and long sunken rift valleys that once pulled Gondwana apart. Some scientists even see circular gravity lows that whisper of ancient impact scars, where asteroids punched deep into the crust and left dense, disturbed mantle beneath. This is the stage on which today's anomalies are playing out, a shattered plate margin still flexing, hidden under a frozen shell. Then we watch the present-day drama. Here the scar is moving, ice is thinning, fast ice streams are shooting toward the ocean, subglacial lakes are filling and draining in slow pulses, and the crust itself is rebounding upward by centimeters per year as the weight comes off. Mass is sliding, lifting, flowing. GRACE measures the loss as a steady dimming of gravity over West Antarctica, while denser mantle rock wells upward to partly fill the deficit. The result is a live experiment in geophysics, a tiny echo of the fireball the whole cosmos was born from, except this time the collisions are between ice, rock, and water in a planet-sized machine. Finally, we confront the void those changes point toward, a future in which sea level does not creep but lurches, in which the poles wander faster as the planet's weight redistributes, in which the gravity field that shaped our tides, our climate, even our navigation satellites, enters a new, less predictable phase of its long cycles. The question is not just how much ice melts, it is whether the quiet background field we treat as fixed can itself cross a threshold. Because this is the core tension running under every satellite map and sea level forecast. This is not only a story about melting ice, it is a story about whether there is a limit to how long we can treat gravity, and with it planetary stability, as a static backdrop to human history rather than a character that can wake, shift, and answer our assumptions with a different pull. So we pull back from the data and cut hard to silence. A stark title card burns onto the screen, under the white wall. The letters sit motionless over a slow, gliding pan across an endless horizon of ice. No trees, no buildings, no motion, but the wind scratching snow across a flat, blinding plain. It feels less like a place on Earth and more like the exposed skull of a planet, scraped bare and left to freeze. This is the surface story of Antarctica, a white wall. Up to 4 kilometers thick in places, a single sheet of ancient ice spread over an area larger than the United States and Mexico combined. Temperatures cold enough to crack steel, air so dry it behaves almost like a vacuum, a desert made of frozen water. From orbit, it looks simple, featureless, clean. It is not simple. Beneath that wall is a hidden continent, a buried architecture of rock, valleys, and water that no human eye has ever seen directly. To reach it, scientists do not dig, they listen. They fire radar pulses through the ice and wait for echoes. They trigger seismic waves and watch how they bend, using the planet itself as a giant ringing bell. What those echoes reveal is something closer to another world. In the heart of East Antarctica, the Subglacial mountains rise jagged and unseen, as tall as the Alps. Their peaks have been entombed for tens of millions of years, yet they still cast a shadow in the data. To the side, deep basins yawn open in the maps, such as Wilkes Land, a dark buried scar hundreds of kilometers across that never sees sunlight and may hold the memory of an ancient impact or the ripped open seam of a continent in the making. This is subglacial topography, a ghost landscape traced not with light, but with time delays and tiny changes in wave speed. And it matters for more than cartography. Every ridge of dense rock, every sediment-filled basin, every pocket of warmer, softer mantle beneath the crust adds or subtracts from Earth's mass in that region. Those differences are invisible to you standing on the ice. To satellites skimming hundreds of kilometers overhead, they are unmistakable. They measure the pull. They feel the bumps and dips in the gravity field, where mountains hide and deep rifts slice the crust. The largest scientific instrument on Earth is not a collider ring or a machine in a tunnel. It is this planet's own shifting interior, rearranging mass and, with it, the strength of the downward tug you call weight. And under West Antarctica, that tug is not behaving. Because among all these buried ranges and basins, GRACE and GOCE found one feature that refused to fit the model: a vast gravity anomaly beneath an ice sheet that is collapsing far faster than its neighbors. Something there is changing mass so quickly that our gravity maps have to be redrawn in real time. What could move a continent's pull on the universe itself? To answer that, we have to go deeper under the white wall, to a place where ice, rock, and mantle plume begin to trade energy, and the ground, very slowly, learns to rise. To see that trade of energy, scientists had to learn to do something that sounds impossible. They had to weigh a continent from space, not with scales or drills or seismic booms, but with a pair of blind machines feeling for the faintest shiver in Earth's pull. The first is GRACE, 2 satellites 220 kilometers apart, locked in an endless chase around the planet. They fly through some of the emptiest, coldest space anywhere in the solar system, joined by an invisible microwave beam. That beam measures the distance between them so precisely that if one satellite moves by less than the width of a human hair over the length of a continent, the change shows up, not as a jolt, as a whisper in the data. Why would they move at all? Because as they fall through Earth's gravity, any extra mass below, an ice sheet, a buried mountain range, a hidden reservoir of rock, tugs a little harder. The lead satellite feels that pull first, surging ahead by a few microns. Then the trailing one catches up. Stretch, relax, stretch. From that tiny dance, GRACE can see mass changes equivalent to draining or filling a large lake, or the loss of hundreds of gigatons of ice spread across an area the size of a small country, all from hundreds of kilometers above the surface. If GRACE is a cosmic scale, GOCE was an underground X-ray, a sleek, dart-shaped craft flown so low it skimmed the very top of the atmosphere, burning fuel just to keep from falling out of the sky. Inside, ultra-sensitive accelerometers felt the slightest uneven tug from hidden mountain ranges and dense mantle blobs, mapping gravity with a resolution down to tens of kilometers. Where GRACE watched the planet breathe in slow motion, GOCE traced the bones and scars under the skin. Together they turned Earth into the largest scientific instrument on Earth, a silent experiment running every orbit. These are not telescopes gazing outward at the early universe. They are blind scouts, endlessly falling around the planet, feeling for invisible wrinkles in the field that holds you to the ground. Every orbit, they send back streams of numbers, tiny changes in distance, tiny accelerations that mean nothing until supercomputers and teams of geophysicists turn them into those surreal, colorful gravity maps. Maps that show where the planet is heavier, where it is lighter, where mass is on the move. When the data first focused on Antarctica, the picture refused to stay still. Year after year, West Antarctica dimmed in gravity, as if the continent were breathing mass out beneath the ice, not a static block of frozen rock, but a restless system where melting ice, rising crust, and deep mantle flows were all tugging at the satellites. The question was no longer whether Antarctica was changing. It was what exactly was powerful enough to leave a scar in gravity itself. To answer that, we have to peel back the ice and follow the anomaly down into the rock. Peeling back the ice starts with a pair of machines chasing Earth's gravity through some of the emptiest, coldest space anywhere in the solar system. Since 2002, the GRACE mission has flown 2 satellites in a tight ring around the planet, one following the other a few hundred kilometers apart, racing through the thin vacuum in perfect formation. When they pass over a giant mass on Earth, the leading satellite is tugged forward first, then the trailing one. By tracking that tiny change in distance, millimeters over hundreds of kilometers, GRACE turns invisible gravity into a moving map. Over West Antarctica, that map began to fade. Year after year, GRACE saw the same pattern. The gravity field over the West Antarctic ice sheet was shrinking. The numbers were brutal. Hundreds of gigatons of ice were vanishing every year. A gigaton is 1 billion tons. Imagine carving out a single ice block as tall as Mount Everest, wide as a major city, and dropping that frozen mountain into the ocean. Now do it again next year, and the year after that. All of that mass was not disappearing. It was moving from the high, cold plateau into the sea, where it helped raise global sea levels and subtly rearrange the mass of the entire planet. The change was so large that GRACE could see it directly as a weakening of gravity, a literal lightening of West Antarctica. Less ice means less pull. With every gigaton lost, the downward tug on passing satellites slackens, the ocean's surface relaxes a little, and regional sea level patterns shift in ways that have to be fed back into navigation systems, climate models, even the quiet corrections that let your smartphone GPS know where down actually is. The whole machine of modern measurement depends on knowing how Earth's mass is arranged, and West Antarctica was rewriting that arrangement in real time. That should have been the end of the story. Melting ice, less gravity, A clean, if unsettling equation. But the data refused to stay simple. In some sectors of West Antarctica, GRACE did not see gravity dropping. It saw gravity rising. In places where the ice sheet was thinning fastest, the pull grew stronger, as though something denser, heavier, was pushing upward to replace the missing ice. The signal looked less like a vanishing cap of frozen water and more like a buried weight being hauled closer to the surface. The largest scientific instrument on Earth had already shown us a fraction of a second after the birth of the universe by smashing particles together in a giant tunnel. Here, another precision machine was revealing a slower planetary collision, ice, rock, and deep mantle trading energy in the dark. If the surface is losing mass while gravity grows stronger, then the real movement is happening below the ice. The only question is how deep that movement goes, and what exactly is rising to meet it. 21:18, when rock flows like honey, Earth's rebound. To understand what is rising, you have to imagine the ground itself behaving less like stone and more like memory foam. Press your hand into a memory foam mattress and it yields, slowly swallowing the weight. Remove your hand and it does not snap back. It creeps. The imprint lingers, then, millimeter by millimeter, the surface climbs toward where it used to be. Earth's crust under Antarctica is that mattress, and the ice sheet is a hand that has been pressing down for tens of thousands of years. An ice sheet a few kilometers thick is not just heavy, it is a planetary scale load, a frozen mountain range spread over a continent, forcing the crust downward and squeezing the mantle beneath it aside. For as long as the ice sits there, the deep rock flows away from the pressure, oozing in slow motion, the way glass bends under its own weight over centuries. When the ice thins, that buried flow begins to reverse. Geologists have driven metal rods deep into West Antarctica's bedrock and crowned them with GPS receivers, turning the continent into a silent array of sensors. Those instruments show something astonishing. In places near the Amundsen Sea and Thwaites Glacier, the crust is rising several centimeters per year. That is among the fastest uplift rates on the planet. What textbooks once treated as a process measured in millimeters per decade is now unfolding at a pace you can track between field seasons. This is isostatic rebound in real time, the deep earth answering the loss of ice. As the overlying mass shrinks, viscous mantle rock flows back, heaving the crust upward. Rock is not supposed to move this quickly, yet it does. And here is the twist. Losing ice should weaken gravity above that region. Less mass, weaker pull. But as the mantle surges upward, denser material creeps closer to the surface, partially replacing the weight that melted away. In some sectors of West Antarctica, the gravity field is stabilizing, even ticking upward, not because the ice is recovering, but because the interior is quietly reloading the column with heavier rock. That rebound is not just a bookkeeping correction in Earth's gravity field. When the crust flexes, it tilts the hidden landscape beneath the ice, steepening some valleys, flattening others, subtly reroading the thin films of subglacial water that lubricate fast ice streams. Change the slope and you can change where ice accelerates, where it stalls, and where the next major collapse front will form. What should be a story written over centuries has been compressed into a decade of satellite passes and GPS logs. The mantle here is responding on human timescales, hinting at warmer, softer regions below, places that, in their own way, behave like some of the emptiest, coldest space anywhere in the solar system. Extreme, fragile, and exquisitely sensitive to small shifts in energy. If the rock is already moving this fast, the next question is unavoidable. What happens when the heat beneath the ice joins the game as well? Heat is only half the story. The other half is water. Beneath Antarctica, the world's largest block of ice is not frozen solid. Under kilometers of pressure and a quiet trickle of geothermal energy from below, the base of the sheet reaches the melting point. Thin films of liquid spread along the bedrock. Pockets deepen into lakes. Rivers thread through the dark. One of them feeds Lake Vostok, a hidden inland sea the size of a small country, sealed under more than 3 kilometers of ice, held in place by weight and silence. These lakes do not just sit there. They fill, they drain, they refill, sometimes over a few years. GRACE watched the gravity above certain parts of East and West Antarctica pulse as subglacial basins suddenly dumped billions of tons of water downstream, then slowly recharged. On the surface, nothing moves, no waves, no storms. Deep below, mass is being shuffled through a buried plumbing system, turning the base of the ice sheet into a giant pressurized machine. Where that water concentrates, the ice above begins to slip. Narrow corridors of ice break free from the slow, grinding flow and surge toward the sea at kilometers per year. These are ice streams. The ones feeding Thwaites and its neighbors behave less like a static glacier and more like frozen rivers, channeled along soft, wet beds, a few tens of kilometers wide, hundreds of kilometers long. They funnel most of West Antarctica's mass loss through a handful of outlets, as if the continent had veins. When a subglacial lake drains beneath an ice stream, the effect on gravity is small in absolute terms, but not invisible. A few meters of ice thickness lost here, a column of water shifted there, and suddenly the local density field changes. To GRACE and its successor missions, those changes show up as tiny flickers in the map, specks of blue and red where the pull of the planet grows weaker or stronger from one year to the next. It is gravity, breathing. Then comes the deeper complication. The rock itself might be hotter than it should be. Several studies combining seismic waves with gravity anomalies point to a region beneath West Antarctica that behaves like a mantle plume, a column of buoyant, warm rock rising from depth, not enough to create temperatures hundreds of thousands of times hotter than the core of the sun or anything close to the hottest place in the entire solar system, but enough to thin the crust, raise the geothermal gradient, and keep that hidden hydrology alive. Put all of this together, and the anomaly starts to look less mysterious and more terrifyingly coherent. A rifted, thinned crust, a possible plume leaking heat, lakes that drain in the dark, ice streams that race toward the ocean. In GRACE and GOCE's reconstructions, West Antarctica stops resembling a stable ice cap and starts to look like a restless, leaking wound in the planet's shell, a place where gravity is not a constant, but a symptom. The question is how quickly that wound can open. To see how deep that wound might go, you have to leave the restless West and cross the buried spine of the continent, into East Antarctica, into Wilkes Land. On a gravity map, Wilkes Land is a bruise that glows. A vast circular positive anomaly hundreds of kilometers across, sitting under kilometers of ice and crust that should be thick, old, and quiet. Instead, the gravity there is higher than you would expect. Something dense is pulling harder. When the first satellite models lit it up, one idea arrived almost instantly: impact. Imagine an asteroid tens of kilometers wide slamming into the early Antarctic crust, punching through the outer shell, driving mantle rock upward in a frozen, permanent rebound. The crater itself would be buried, eroded, consumed by later ice. But the dense, uplifted mantle, the fractured ring of broken lithosphere, would still whisper its presence to gravity, a tiny echo of the fireball the whole cosmos was born from. Not everyone buys that ancient catastrophe. There is a quieter explanation. East Antarctica has been stitched and torn by supercontinents assembling and breaking apart. An old rift zone, deep crustal thinning, or the roots of a lost mountain chain could concentrate denser rocks at depth and raise the local gravity, no asteroid required. In that view, Wilkes Land is not a scar from a single terrible day, but a palimpsest of slow tectonic violence written over hundreds of millions of years. Now contrast that with the West. There, GOCE's high-resolution data revealed deep, elongated basins, aligned with known rift systems, places where the crust is thinned almost to transparency, and denser mantle rises closer to the surface. Those hidden trenches create gravity highs from below that coexist with gravity lows from above, where GRACE watches ice mass vanish into the ocean. The result is a gravity field that looks less like a smooth planetary shell and more like a shattered ring around the South Pole. GOCE sharpened every edge. Its measurements traced sharp gradients and strange offset shapes that do not neatly follow the mountains we can see or the coastlines on a map. Under the ice, it hints at old suture zones where continents collided, at mountain roots that no longer have peaks, at possible impact scars that never quite healed. The planet begins to resemble a cathedral built to worship a single question: what happened here? Yet the core argument remains unresolved. No drill has punched through the ice and rock of Wilkes Land to sample a buried crater rim. No seismic image has ended the debate. Is that gravity scar the frozen memory of a world-ending collision, or the slow grind of plates and rifts rearranging a hemisphere? That uncertainty is not academic. The deep architecture decides where the ice above will crack, where meltwater will focus, where collapse will race. And in the next part, the gravity field stops being a map of the past and starts to become a forecast of failure. When gravity moves, shorelines move with it. Not tomorrow, not in some abstract geological future, but on the timescale of levee upgrades, mortgage terms, and a child born today. The invisible scar under West Antarctica is not just sculpting ice, it is already sketching new coastlines. Here is the paradox. When a giant ice sheet loses mass, nearby seas do not simply surge upward, they can fall. An ice sheet is a mountain of frozen rock and water, and its mass pulls the surrounding ocean toward it. A quiet tug written into the planet's gravity field. As West Antarctica thins, that local pull weakens. Ocean water is released, pushed away by Earth's rotation and drawn toward regions where gravity now wins the tug of war. Scientists call the pattern that follows a sea level fingerprint. Close to the collapsing ice, the sea can actually drop relative to the land. Far away, thousands of kilometers across the globe, the same loss of ice translates into an amplified rise. The fingerprint of West Antarctic melt does not point at Antarctica, it points at the rest of us. In practice, that means some of the most vulnerable cities are not those staring directly at the ice wall, but those on distant, crowded coasts. New York, Boston, Miami, Rotterdam, Shanghai, all sit in the far field of Antarctica's gravity. As the southern ice drains away, these coasts inherit more than their fair share of sea level rise. Meanwhile, parts of the Southern Ocean, hugging the shrinking ice sheet, may see a relative fall, a counterintuitive dip created not by safety, but by a vanishing gravitational anchor. The redistribution does not stop at the shoreline. When trillions of tons of ice migrate from the poles into the oceans, Earth's mass shifts outward. The planet's moment of inertia changes, the same way a spinning skater slows when they extend their arms. The rotation axis nudges. The length of the day stretches by fractions of a millisecond. Tiny changes. but measured daily by satellites that live in some of the emptiest, coldest space anywhere in the solar system. Those measurements hint at something more dangerous than gradual drift. West Antarctica is laced with grounding lines and buttressing ice shelves that behave less like static walls and more like the supports in a cathedral built to worship a single question: how long can this remain standing? Cross certain thresholds, remove just enough support, and retreat becomes self-sustaining. Cliff faces of ice crumble, glaciers accelerate, and meters of sea level rise can be unleashed over mere centuries, not the slow crawl of an ancient climate cycle. We are watching this play out in real time. Human-driven warming is pushing a major ice sheet toward instability, while orbiting machines quietly log the consequences. The ice surface sinking, the crust rebounding upward, the gravity field itself rewiring. The last time Earth's mass shifted this fast, the early universe of human civilization did not yet exist. Now, with every new satellite pass, we are forced to ask what happens when the force that holds the oceans in place starts to move beneath our feet. In the next section, the camera will dive from orbit back down into the fractures and hidden currents that decide how fast that question is answered. From orbit, it began as a glitch, a slight unnerving deviation in the satellite's path, as if the planet had exhaled under Antarctica and the pull of the ground had changed. We followed that deviation down through the atmosphere, through the cold, thin air and the drifting snow, and then through the ice itself. Under the white, there was structure, ancient mountain ranges frozen into silence, rift systems yawning beneath kilometers of ice, dense scars in the mantle where something enormous had once struck and sunk. GRACE and GOCE did not see them with cameras. They felt them as changes in the invisible field that wraps the whole world. In a human lifetime, ice, water, and rock had shifted enough mass to redraw the map of gravity. That is the core revelation of this journey. Gravity is not just a constant that quietly keeps your feet on the floor. It is a living record of how mass moves through the Earth system, a ledger written in microgals and millimeters. When West Antarctica sheds gigatons of ice each year, GRACE watches the gravity there fade. When the crust underneath rebounds upward by centimeters per year, GOCE senses the rising rock as a new tug on its orbit. Ice collapses. Mantle plumes swell and rise. Subglacial lakes migrate and drain. The field responds. Among all the signals humming through that field, Antarctica is currently the loudest place on the record. For most of our history, none of this existed for us. Earth was a stage, not a character, a stable platform on which civilizations could build ports, lay tunnels, and draw coastlines as if they were permanent. Now, the instruments we have buried in the crust and launched into some of the emptiest, coldest space anywhere in the solar system are sensitive enough to show that the platform is flexing, rebounding, and occasionally lurching beneath our cities. That double message is hard to ignore. On one hand, the fact that we can detect crustal uplift measured in centimeters per year or track ice loss in gigatons per year is a triumph of the same scientific culture that built the most powerful machine humanity has ever built to study particles a fraction of a second after the birth of the universe. On the other, the trends those measurements reveal are a warning. We are pushing a dynamic system toward regimes no human infrastructure has ever been tested in. The real story is not that something under Antarctica is rewriting gravity. It is that gravity is writing back to us. In the slow tilt of shorelines, in the shifting paths of satellites, in the quiet acceleration of sea level rise, the field is spelling out how long we can pretend the planet is a static backdrop. The question now is whether we can learn to read that message in time. Because in the next section, The camera will leave the abstract field and drop into the human world that field is already rearranging. So bring it back to where you are now. Your feet on a floor, your weight in a chair, the quiet, invisible pull that tells your inner ear which way is down. The same gravity field that is being redrawn under Antarctica is the field holding your body in place at this exact moment, threading through bone and blood, through the device in your pocket, and the orbiting machines that guide it. When your phone finds its position, it is already correcting for that shifting pull. GRACE and its successor, GRACE FO, have watched West Antarctica lose so much mass that the local gravity has measurably weakened, and those changes are now baked into the GPS signals that tell you where to turn. Tide gauges along coasts you may never have seen are quietly registering millimeters of extra water, in part because an ice sheet thousands of kilometers away has relaxed its grip on the ocean. Picture a different pair of feet. A child stands on a seawall in a city that has never seen Antarctic ice. The air is warm, the concrete is sun-bleached, and the ocean below slaps against the barrier just a little higher than it did in old photographs. Each decade, the line creeps up. A step on the seawall closed, a playground moved inland, a basement that floods on spring tides. That child will grow up never knowing that part of the reason is a ghostly gravity fingerprint from a collapsing sheet of ice on the far side of the world. We have built machines that can feel that fingerprint. Not the most powerful machine humanity has ever built. Not a giant ring in a tunnel, but constellations of satellites sliding through some of the emptiest, coldest space anywhere in the solar system, watching the planet's mass shift gram by gram. They listen to the tiny changes in their own orbits, and in that silence they can feel the planet breathe. Over Antarctica, that breath is quickening. The crust is rebounding centimeters per year. The mantle is flowing. Subglacial lakes are filling and draining under a lid of ice. It is as if the deep interior and the frozen surface have entered a new conversation, and our instruments are just close enough to overhear the first sentences. So treat the gravity maps, the ice loss graphs, the rising sea curves not as distant abstract science, but as early subtitles in a story that will redraw coastlines, economies, ecosystems. Follow the missions that are writing those subtitles in real time. GRACEFO, IceSat, ICE2, the next generation of Antarctic surveys that will stare through the ice and watch the bedrock move. Because if this is what we can already see, gravity fields warping, continents rebounding, ice sheets destabilizing, what will we find the next time our machines report that somewhere on this moving world, the pull beneath our feet has quietly changed, and the story has turned a page we did not know was coming